Now let's dive our way into the atmospheres and talk about what we do understand. And for the gas giants, as always, there are very similar structures here. The way to read this chart is that each value here is a depth in thousands of kilometers. So this here means that at 59,000 kilometers underneath the gaseous surface, you'll get this distinction between what's called molecular hydrogen and metallic hydrogen. The metallic hydrogen is going to be very important for us, especially when we start talking about the magnetic fields produced by the giant planets. So let's go back to this top layer. The molecular hydrogen, which is about 71,000 kilometers above the core of the planets. This molecular hydrogen just means hydrogen that's been squeezed, compressed enough that it's formed molecular bonds with itself. Down below that, you get to that very important metallic hydrogen. What this means is that this is hydrogen that is conducting electricity. Electrons are free to flow through this pseudo gas liquid mixture. Underneath that, we're going to find layers of these ices and rocks. Now shifting over to the ice giants. And just from our perspective, here's a scale Earth. So the core of the giant planets are bigger than Earth itself. Even though, switching to ice giants, they'll still have these layers of molecular hydrogens, followed by our icy and rock layers. And by ices, we predominantly mean ammonias and methanes that are frozen there. And you're going to find these deep oceans in the liquid parts of this dissolved gases and salts. So there's this crazy complex chemistry soup happening even in the ice giants. Now let's begin our discussion on the magnetic fields of the giant planets. And for the bulk of our discussion, we're going to refer to just Jupiter. So here's an image of Jupiter's magnetic field. So for perspective, here's Jupiter here in the center, and it has these magnetic field lines that go out and around the planets. This should remind you of Earth's magnetic fields, or another term we'll frequently use is the bar magnets here. You've got a North Pole coming around, these bands coming back. Now the density of the field lines tells us how strong the magnetic fields are. And in fact, the magnetic field lines on Jupiter are so strong that it creates this torus shape, basically as donut, of charged matter trapped around going in a circle. So remember this discussion when we talk about charged matter going in a circle. That'll come back around for us. But let's look at the even bigger scale here. And here's the image of Jupiter's magnetosphere, and Saturn has a similar one. And Jupiter's magnetosphere extends almost 6 astronomical units behind it, creating this gigantic magnetic wake around it. One of the important things about our solar system is that Jupiter is basically this great big defender of planet Earth. Its huge mass protects us from any stray objects trying to slam into us, because Jupiter tends to absorb that, literally absorb it. We constantly see things impacting Jupiter's atmosphere. And Jupiter's nice strong magnetic field also acts as a shield from stray cosmic radiation. Now, keeping up with our analogies of things we see on Earth due to Earth's magnetic field, oh yeah, there's definitely auroras on the gas giants. Beautiful spectacles here. Here's one of Saturn, and you're seeing them simultaneously happening on the poles of Saturn here. As a reminder, the auroras are charged particles interacting in the magnetic fields, and that charged particle will come in, and the magnetic fields will deflect it, and if there's enough, if they're moving fast enough, they'll eventually hit where the magnetic fields are strongest and tend to just barge in, just break through and flux. They'll just constantly irradiate the atmosphere there, and you get these gigantic, beautiful auroras on the gas giants. Recall what I said about the torus around Jupiter, how the magnetic field lines can trap a string of charged particles floating around. So, a consequence of that is what we call this synchrotron radiation. here's the principle. What's going on here? Take one of those field lines, and here I've marked it with just the magnetic field line being this red arrow. So there's magnetic field present here. And now I'm going to shoot a charged particle. In the diagram, I chose an electron, but to be complete here, it has to be just any charged particle. It could be a proton, it could be helium, and it just is missing some electrons. It could just be some stray ions. Doesn't matter. As long as it's a charged particle, that's what's going to matter here. Now, coming back around here, why pick electron? Well, that's just the most abundant thing you're going to find. That's the easiest charged particle to have flying around space. So what happens is that this electron initially had some kinetic energy going one direction. And then it interacts with the magnetic field, magnetic forces act on that electron, and that forces it to spiral. So now I have an electron that's propagating downwards, and because of its interactions with the magnetic field, creating a spiraling pattern. Now think back a bit. Let's go ahead and add a little axis here. And I'm going to look at, well, what is the electric field here, 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 so on, as the electron goes by. An electron goes by each one of these individual points. You're going to have a big electric field, big electric field, big electric field. But when the electron goes away, you'll have low, low, low. So the electric field, as a function of time, is oscillating. Electric field will go high, then low, high, low, high, low, so on and so forth. This should remind you of a discussion we did many sections ago, in section 5, on light. The electric fields are oscillating up and down like so, and talk about electromagnetic waves. What is it? It's a combination of oscillating electric fields and magnetic fields. Maxwell's equations tells us that, hey, if there's a change in electric field, there must be a corresponding changing electric field, and vice versa. So as this electron is propagating down the magnetic field, going in circles, it's literally producing photons. You're creating electromagnetic waves that generally are in the radio wave spectrum. So a consequence of all this, Jupiter literally glows in a radio spectrum. So these lines here are marking out the dimensions of Jupiter, but because of those flux lines, that synchrotron radiation, the entirety of Jupiter has this radio wave glow because of charged particles getting trapped inside Jupiter's strong magnetic field and radiating radio waves as they propagate around. Now, one last topic that we'll only briefly talk about in this video is this concept of planetary migration. So here in the pictures, we're representing what's happening of how the gas giants and the ice giants formed, and take a large collection of gas, dust, and particles, and accrete them down into the various giant planets. And this doesn't match the hot Jupiters that we're consistently finding out across the other stars. Now remember, the hot Jupiters, these were Jupiter or even bigger sized planets very close to their host stars. We've seen planets that are 10 times the mass of Jupiter, the distance of Mercury away their host star. And that just doesn't match with what we understand about the formation of the giant planets, or the gas or ice giants. So one concept that's been proposed to explain this is this idea of planetary migrations. And basically, in essence, is that you have your giant planets out here, and over the millions or billions of years, you'll have these slight perturbations, different gravitational influences that cause those to migrate closer and closer to their host star. So here our principle, this idea we have of what creates those hot Jupiters, like the one we saw at the very beginning of this lecture, is a hot Jupiter, which is a Jupiter, a gas giant like we see in our solar system, that had enough gravitational quirks that drove it in towards its host star. So summarizing a little bit of what we talked about in these videos, one thing to emphasize here is that mathematics has predicted the location of multiple planets and multiple objects out there. Heck, the very existence of that strange concept of dark matter only exists because we've measured it, we've seen it's a consequence out there. So we don't fully understand the picture, but we can see consequences and predict things about it. You can use tricks like stellar occultation to measure the size of giant planets, and at least on the gas giants, we have seen storms that have lasted for many years, potentially centuries. And their large magnetic fields are produced by that metallic hydrogen that's swirling around, unlike what's happening on Earth, where you have these ferromagnetic cores rotating around. On the gas giants, you have this metallic hydrogen that's swirling around rapidly, producing these gigantic magnetic fields, and those magnetic fields can trap ions that will radiate radio waves in a process that we call synchrotron radiation. So pulling this all together, there are still lots that we don't understand about the giant planets, like the wind patterns, what's unique and distinguishing between all of them, and what produces their different wind patterns. So there's still plenty to learn about the giant planets, and lots that we can definitely observe by crashing satellites into them. So that, we'll call it into section 10, and I'll see you all next time.